introduce the next speaker. So I hope we have our next speaker coming from RMIT. Kenneth, if you are there, if you can share your screen and start the presentation about the user.
Good morning.
Electron. Hello.
Hello. Let me share my screen.
Oh, hello, Jun. So
yes.
Over to you.
Okay. Good morning, everybody. Can you see my screen?
Yes.
Yes.
Thank you.
Okay. I'm Kenneth Peck. I'm from RMIT University, and good morning. I would like to today I would like to introduce our research work. The title is the use of electron migration media as moisture sensor for building structure health monitoring. And I'm the student of Professor Jack Lee. He's from the School of Engineering and of RMIT. So let's take a look what I'm going to present today. First of all, I believe all of us well know what is reinforced concrete and water. But the point is, what is the problem when they meet together? And then when water meet with reinforcement inside the concrete, what will happen? I believe all here are engineers where we know about what will happen is corrosion. But so how the water comes, where they comes, why there's water inside the concrete? There's a big problem in our buildings. So can we identify the source of the water? So in this presentation, I would like to introduce a method to identify the source of water from the external, for example, the roof and external wall of the building. So here's the problem. I'm from Hong Kong. This is some photos of our city. You can see at the left-hand side, there's new buildings and some old buildings. They locate side by side. And then on the right-hand side, you can see there's a redeveloped buildings, where high-rise residential buildings with some old buildings in the front, and it is its old area. And what's the problem in our building? Actually, it's water seepage. You can see here, it is a rooftop of a residential building. You can see there's some tiles on the top, and then there's some surface drains around the parapet of the roof. So from our cases, we have studied a number of cases in this kind of buildings, and we found that the major problem will be the surface drain. And sometimes there's sometimes leakage from this the edge of the tiles, the leakage of water, and then they seepage into the reinforced concrete. You can see here there's some example in Hong Kong. We found that water seepage problem in our building. You can see on the left hand side, you can see there's some vegetated, and then there's some water staying along the edge of the building, and also there are cracks. Okay, on the right hand side you can see the tile already detached, and then the water vegetation. And actually, this case is very similar in Hong Kong, and you can see, for example, for those residential building with maybe 30 years old, it's very common situation in Hong Kong. I believe that there is a similar case in the city in other country, and also in Australia. So this is the indoor condition of those buildings. You can see there's spoiled concrete, and you can see the water seepage from the roof, and also the wall. This is red. We measured it with some moisture meter over there. The moisture is very high. So let's see why there's water go into the building. You can see it here. There's a typical detail of the rooftop. You can see from the drawings, we have a tile at the top, and some insulating layer, and then there's you can see there's a band right layer. This is we call it a waterproof membrane, and then there's some cement mortar as at the bottom. Before, and then you can see the mortar is just above the reinforced concrete. The problem is that the water comes from the surface of the roof and then penetrated through the tile, and then somehow they when the waterproofing layer deteriorated, the water penetrates and then goes into the cement plaster and also the reinforced concrete. So the problem is that the rooftop was damaged due to water ingress. So here I summarize some method we are currently used to determine the presence of water in reinforced concrete. So first of all, we have infrared thermography on the right hand side, and then we have a water bonding test. Actually, maybe I give more details about water bonding test in what we've done in Hong Kong. Now you can see from the picture on the left hand side, this one. You can see alternation. They try to make a water pond in the suspected area, and they try to add some colored water on the floor slab, and try to add some water pressure on the floor. So if there's crack or seepage, then the colored water will penetrate into the concrete, and then they can see the colored water at the bottom side of the slab. That means the ceiling of the floor below. So that's the current practice we did in Hong Kong. And then we also use the moisture measurement method. So for example, there's a moisture meter at the center of the on the picture on the center, and also we use a moisture meter to determine the moisture condition of the reinforced concrete. So the point is, we found that this kind of NDT methods, actually there's some query about their efficiency and accuracy, and also actually there's very poor. For example, the moisture meter, they just measure the surface moisture content. Actually, it's not representing the condition of a whole reinforced concrete, because it is a mass of it's a concrete mass. But the moisture meter just measures the surface moisture content. It's not. It's some kind of indication to the engineer, but not the full picture. And also we found that all these methods are unsuitable, inaccurate, and costly, and too passive. In other words, it's too late. The reason why we can refer to the previous picture, we found that there water seepage or even concrete spoiling, and then we identify engineer to go to the building and try to identify the source of water, but it's too late because the building deteriorated. There are concrete spoiling of the reinforced being corroded. It's too late. Is there any method that is more smart? So on the other hand, we have some experience on common NDT. For example, the very extensive use is the microwave moisture meter, moisture measurement. You can see here there's a picture showing that there are 6 numbers of devices we collected in Hong Kong, and we did some research on this device. The people in Hong Kong, they are trying to use this device to measure the average moisture content inside a concrete mass. But from our study, we found that this device is quite good in mass concrete, but we are working with reinforced concrete, and the device is based on EM wave. So the reinforcement interfere the result. So that is not quite accurate in the actual measurement, and our study showing that there's we need some more works before we say that the method is helpful and it is reliable. So it's not a fully developed method, And then I think it is a good indication, but it still cannot tell us where is the source of water. So we need a new approach to identify the source with a smarter, it's early warning, and then real-time method. And most likely is most important is to be user-friendly. So our ideas is to change the property of the cement mortar, which just located on the surface of reinforced concrete. We can recall the details as I showed in the previous slide. There's a thin layer of cementitious mortar just above the reinforced concrete. So we replace that thin layer of cement mortar with an new material. We call it electron migration media, EMM. So what is that? Actually, this is a new type of cement mortar with a better conductivity. You can see here when the EMM was dry, originally was dry. They have maybe a certain degree of conductivity. When it being moist, the conductivity changed. For example, the voltage, the resistance, and its impedance, they changed. So by measuring the difference in the impedance, we can find that the concrete being moist. The cement mortar being moist. So the whole idea is behind is that actually it's the EMM is just a traditional cement mortar with the addition of graphene and then some other additives to make the EMM, so that the cement mortar being more conductive as compared with traditional cement mortar. So here you can see a picture from our laboratory work. You can see that we cast a thin on the right hand side of the picture. We cast a panel with the EMM with some conductive copper. This is a copper. This is make the channel so that you input the voltage inside the panel. And also we found that with the EMM, because it is graphene, we improved the tensile strength of the cement mortar, and also it's lighter in weight. It's only about 18.5 kilonewton per meter cube. So in the next slide. So this is a schematic diagram of the EMM system. You can see that actually this is the reinforced concrete slab, and you can see the dark gray is the EMM, and also the waterproofing membrane shows in yellow, and the floor tile in light gray. So we input voltage from the left hand side or right hand side, and then we measure the voltage on the other side. The voltage and also the frequency and the resistance will determine the impedance of the EMM and input to a computer system. And so when we repeatedly measure the impedance of the EMM, so we can monitor the moisture condition inside the EMM. So once there's a moisture in the EMM, so the system will alert there's a water increase. So we did a try on the panel. You can see here. So on there along, you can see there's some the copper plate along the panel. You can see we try to input a voltage from the channel 44 here. So we measure the impedance along channel 1, 4, 7, 10, so on. And before we add moisture, the voltage is here. Once we get we add moisture on the surface of the EMM, just like here, and then we found that there is a change in the voltage. You can see here. We compare the differences. You can see that there's it's obviously the voltage between channel 44 and 1 to 15, there's a significant increment. It's about 10% increment on the voltage. So the EMM can tell you there's a moisture, but how to locate the position of moisture? There's another point we have to solve. So we borrowed some techniques from medical use. I believe some of us may use the technique CT scan for our body. Just show on the left, on the picture on the left hand side. So it's similar to CT scan. We measure, for example, there's a moisture on the roof. We use the channel 1 to input voltage inside the EMM and measure the impedance along other channels, and then we got some data. And then when do a progressive scan along all the channels, then we can have a mesh, and then we can use the computerized tomography idea to locate the location of the moisture. So there's the whole idea of the EMM. And up to this moment, we found that the result is quite promising. And in the next stage, we're trying to use some more tests on the EMM panel to validate the method. And also, there's a point is we have to determine the uncertainty and the threshold of the method, because we have to know the degree of moisture to trigger the EMM to show that there's to trigger the change in impedance of the EMM. So, and also have to develop a system so that the management office of the building can have a warning signal when there's a water leakage on the roof. And also at last, we try to have a full-scale trial panel so that to test the method. And that's the end of my presentation. Thank you very much.
Thank you, Kenneth. Really great presentation, and it's really
Thank
important topic. I heard, I remember that up to 40% of the damage is in buildings is related to water seepage problem. So really important to address that. So thank you.
Yes, thank you.
So
thank you.
Hope to hear any comments, any question to Kenneth. I have a quick question just regarding this method. Is it going to be difficult to apply in, let's say, in high-rise building? And what would you think about the cost of applying that?
Oh yeah, that's a good question. Actually, for existing building, it's quite difficult to apply the EMM because all the roof being actually this is an existing roof, and the installation of EMM you have to re-roof. Actually, we remove all the proofing and all the cement mortar on the top of the reinforced concrete. Actually, it's a big project. But for new buildings, we can use this technique when it built, because from my point of view, that we can do. I think we can do limited work for existing, but for the new building, where I think it's very important for the management office to know the condition of the roof. So and other question is about the price, the cost of installation. We checked with some contractor in local in Hong Kong. Actually, we conclude that the price of the consultant cost of the roof will be increased slightly, about 10%. It's only about 10% because the cost of grafting is not that expensive. But the point is the installation, the workers should be well trained, because the mixing of EMM is quite complicated. It is actually with some specialized mixture, and then Also, you have to install some sensors along the edge of the roof. So once installed, the whole roof become a big sensor. It will be a large piece of sensor, and then actually we believe that with the CT, every inch of the roof can be monitored by the system. Since the whole piece of concrete become a big sensor. Yeah.
Excellent, thank you. I think we probably need to move on. I'm sure if you have any question, you can ask Kenneth, even through the chat box.